Welcome to AP Calculus. This is our review for Chapter 3 test, and this will be done in parts. I'm not certain if it'll be 2 parts or 3 parts. We'll see how it goes. So question number 1 says use the definition of derivative. So the definition of derivative. We're about to grow out of this. We should be excited about that when we're going to be using derivative shortcuts. In fact, for most of this test, you're going to be able to use derivative shortcuts. But on the first page, you've got 2 problems that will be similar to these, and we're going to go through the definition of derivative. That is, the limit as h approaches 0 of f of x plus h minus f of x on h. You may also see this referred to as difference quotient. If it says use the difference quotient to find the derivative, that is what they're referring to, quotient of differences. And this is actually in the bottom, you could think of this as x plus h minus x. So this is just our slope formula. So when I put x plus h into this function, if I want to refer to this as function of x, if that helps, f of x. F of x is a factor that takes things, puts them right here and right here. So I get the limit, and you're going to have to write fairly small on this, on the test. The limit as h approaches 0, and we need to write limit every time. We're not going to shortcut that. Of negative 3 times x plus h gets squared plus 5, and x plus h gets here. And I've seen people before they get to there and think they've got enough on the numerator already, but that is just f of x plus h minus all of f of x. And f of x is negative 3 x squared plus 5x. Now, if you want to save a little room, we could put this over h here. If you want to save a little room, one thing you could do, maybe it'd be better with the bracket, is just go bracket and divide by h out here. If you think that's going to save you some room moving down. So at that point, limit as h approaches 0, I've got some simplifying to do. So I'm going to do this, and I'm going to take care of all of this in one step. Take 2 steps if necessary for you. But when I FOIL x plus h, I'm going to get an x squared times negative 3. I'm going to get 2 xh's times negative 3. And I'm going to get an h squared times negative 3. I'm going to distribute the 5, so plus 5x plus 5h. I'm going to distribute the negative, so plus 3x squared minus 5x. And all of that is still on h. Now, at this stage, I'm expecting some good things to happen. Here, let's take a look. Limit as h approaches 0. I've got a minus 3x cancels a plus 3x. I've got a plus 5x cancels a minus 5x. All of the rest of my terms in the numerator have a factor of h, which I'm going to cancel with this h, so I'm left with minus 6x, h cancels, minus 3h, one of the h's cancel, and a plus 5, and I've canceled the h in the denominator. At that point, I'm direct substituting 0 in, and I get negative 6x minus 3 times 0, 0, plus 5. Now, the good news is, the bad news is we've got to go through that process when we know the answer, but the good news is you can check. What should our derivative be? Negative 6x plus 5, so I feel good about that. Negative 6x plus 5. So, got another line down here. Let's take a look. Use the definition of derivative to find dy dx, and they were kind enough here to put dy dx equals, but had they not put that there, we should include that as our answer because it's asking for it. Of the f prime of the function y equals f of x. Then find the slope of the curve when x equals 1. Well, this is our slope formula. F prime x, our slope formula, is negative 6x plus 5. Therefore, I want f when x is 1, prime of 1 is negative 6 times 1 plus 5 is negative 1. So then find the slope of the curve. So the slope is this, and write an equation for the tangent line. Well, what do we need for an equation of a line? I need a slope. I've got it. And I need a point Well, I know part of my point. Part of my point is x equals 1. 1 what? Well, don't put 1 into the slope formula. That's our slope. I want the y value. When I put 1 in here, I'm asking for f of 1. F of 1 is negative 3 times 1 squared plus 5 times 1, or negative 3 plus 5, 2. So my equation of the tangent line, ask for it in slope-intercept form. I'm going to go point-slope form. Y minus the y coordinate, 2, equals slope, negative 1 times x minus the x coordinate, 1, or y minus 2 equals negative x plus 1. Add 2 to both sides, I get y equals negative x plus 3. And we may not have time to come back and check that, but if we did, I'd be really interested in graphing. If I had time, I'd be really interested in graphing this versus that and see if it does look like a tangent line at the point 1, 2. Okay, same process, a little bit more algebra involved here. So I want the limit as h approaches 0 of f of x plus h. X plus h takes the place of x here. I get 3 on x plus h minus 2 minus f of x, 3 on x minus 2, all on h. For this, I find my least common denominators. I need a big factor of x plus h minus 2 and another factor of x minus 2. I'm going to multiply top and bottom by x plus h minus 2 times x minus 2, all on x plus h minus 2 times x minus 2. When I distribute this whole package to here, the x plus h minus 2's cancel. And I get 3 times just the x minus 2. Minus this 3, when I distribute this whole package to here, the x minus 2's cancel, and I get just the minus 3 times all of x plus h minus 2. In the denominator, don't forget about it, that happens often, h, nothing cancels. I get x plus h minus 2 times x minus 2. Now, if you think about this and look forward, this is pretty comforting, because if I was to quotient rule this, eventually I would be over the square of the thing below. And look what's going to happen. I expect this h to cancel. I expect to put 0 in here for h, and I'm going to get x minus 2 squared over the square of the thing below. So that's encouraging to me. Limit as h approaches 0. I think I'm going to do all this in my head. I'm going to get a 3x. I'm going to get a minus 3x, cancels. I'm going to get a minus 6. I'm going to get a plus 6, cancels. But I'm also going to get a minus 3h on h times x plus h minus 2 times x minus 2. H cancels. And now I can direct substitute 0 in. Once I direct substitute 0 in, I'm done with the limit sign. This equals negative 3 on x minus 2 squared. So dy dx, negative 3 on x minus 2 squared. I need now to find f of 1, and I need to find f prime of 1. F of 1 equals 3 over 1 minus 2, or 3 on negative 1, negative 3. F prime of 1 equals negative 3 on 1 minus 2 squared, or negative 3 on negative 1 squared, negative 3 on positive 1, or it's negative 3 as well. Coincidental. So my tangent line, this implies we have the point 1, negative 3. So my tangent line is y minus the y coordinate equals slope negative 3 times x minus the x coordinate, or y plus 3 equals negative 3x plus 3. Subtract 3 on both sides, and I get y equals negative 3x. Okay, now, obviously we want to be good at this, but we also want to be efficient. Again, we can come back and check this, but we could also do quotient rule on this, but watch this. What if I thought of this as y equals 3 times x minus 2 to the negative first? A quick chain rule here becomes negative 1 times 3, negative 3, x minus 2 to the, reduce this by 1, negative 2, multiplied by the inside derivative, but the inside derivative is just 1. That quickly I can see that this is equal to that guy, my solution. Okay. Page 2. Use Derive on our calculator. All right, let's clear this guy out and quit here for a second and clear that out. All right, use Derive to find an equation for the tangent line to the curve at the given point. So I've got this function. Yeah, we don't have a shortcut derivative method for this yet. So we're going to find an equation to the tangent line. I need the derivative of this guy. I need derivative of this when x equals 1. So I'm going to go to Math 8 is Derive. I want the derivative with respect to x of 3 to the x plus 1, I think we can see that, minus 1 at 1. And I get this. And on the AP test, unless you're told otherwise, you are to round to 3 decimal places. They actually, I believe, say you can truncate as well, but we're going to get in the habit of rounding. 9.888. So if I call it f prime of 1 is 9.888. Not exactly that, but very close to that. Maybe I should say just about equal to. So use the Derive to find an equation for the tangent line. Well, I also need to find what is f of plain old 1. F of plain old 1, if I put 1 in, is 3 to the 1 plus 1 minus 1, or 3 to the second 9 minus 1, 8, implying that we have a point at 1, 8. So find an equation for the tangent line to the curve. Write the equation of the tangent line in slope-intercept form. So that's y minus 8 equals our slope, 9.888, times x minus the x-coordinate, 1, or y minus 8 equals 9.888x minus 9.888. I think I said an extra 8 prior to that. Add 8 to both sides. Y equals 9.888x. Add 8 to this, and I'm at negative 1.888. Okay. So there we have our tangent line. Provide a sketch of the function. Well, to provide a sketch, I'll just go ahead and do it by hand here. Here's our function. I'm going to do a quick T-chart here. Quick T-chart, I'll put it over here. X, Y, we're graphing this function. I think negative 1 is kind of an interesting point. Put in negative 1, I get 3 to the 0th, 1 minus 1, 0. I'm going to put in 0, I get 3 to the first, 3 minus 1, 2. I'm going to put in 1, I get 3 to the second, 9 minus 1, I already had that one. There's 8. It's going to start growing very fast now. If I put in 2, I get 3 to the third, 27 minus 1. I notice 3 to any power is always going to be bigger than 0, but it can get close to 0, and if I subtract 1, the graph's going to get close to negative 1. So I have a horizontal asymptote here. I've got some points at negative 1, 0. Negative 1, 0. I've got a point at 0, 2. I've got a point at 1, 8, at which point it's getting very, very fast, and I'm getting sucked into this asymptote down here. So there's our graph. Now, we're getting pretty vertical at this, but it's still curving in an upward manner, and this graph, this equation right here, I'm also supposed to graph. It's supposed to be tangent at that point. Passes through y-intercept about in here, and definitely passes through that point. We found that out already. So we are right here, and that red graph would be touching here and peeling away a little bit. Kind of tough to see. Might have been better to have the tangent line in a place where there's a more pronounced curve. But that's it. You can check that on your calculator as well by graphing both of those two functions. Okay, when we have a polynomial and we're to find all derivatives, they're just saying just take derivatives until this just becomes 0. They don't tell us dy dx, so I'm just going to call it y prime. First derivative, this is really, you may want to think of this as 1/12 times. So 4 times 1/12 is 4/12, 1/3 x to the third. Again, please don't go through the whole limit process if they don't ask you to. Minus 2 times 1/2, 1 x to the first, minus derivative of x is 1. And the second derivative is 3 times 1/3, 1 x squared. Derivative of x is 1. Derivative of 1 is 0. Third derivative, I'm just going to keep doing it. I guess I could put a 3 here as well, but I'm going to do it this way with the primes. Equals 2x. Fourth derivative is 2. And the fifth derivative, is 0. So if you wanted, you could dy dx this. So dy dx is 10x to the fourth plus 2x, excuse me. d2y dx squared is 40x to the third plus 2. d3y dx3 is 120 x squared. Fourth derivative is 240 x, getting there. Fifth derivative with respect to x is 240, and the big payoff, sixth derivative of y with respect to x is 0. That should be pretty quick, pretty easy, and successful for everybody taking this. All right. Find dy dx. I'm going to use dy dx here. Find each derivative in two ways by applying the product rule. So here's going to be my product rule first. By product rule, dy dx, don't just say y prime here, they say find dy dx, equals the first term times the derivative of the second, 8x plus 3, plus the derivative of the first, 3x squared, times the plain old second, 4x squared plus 3x minus 7. Simplify. 8x to the fourth plus 3x cubes plus 12x to the fourth plus 9x cubed minus 21x squared, combined terms, and I get 20x to the fourths, and I get plus 12x cubes minus 21x squareds. And it would be really simple to move on to the next problem if we're not good readers, by applying the product rule and by multiplying the factors to produce a sum of simpler terms to differentiate. Okay, so now we're going to multiply first. Then we get y equals, if I distribute this, I get 4x to the fifth plus 3x to the fourth minus 7x cubed. And now dy dx, the derivative of y with respect to x, is 20x to the fourth plus 12x cubed by power rule minus 21x squared. So I think the point being made here is, yeah, it might be better to do the multiplication first if it's convenient. Particularly if we need to simplify. If we could just leave the answer like that, that's not a bad way to do this. So B, let's go product rule. Product rule, the derivative of a function times a function is the just plain first function times the derivative of the second function. I can't tell you how many times I see people not put the parentheses here. It's this whole first function times the derivative of the second. plus the derivative of the first function is negative 5 times the whole second function, 3 plus 8x. Simplify, I get 32 minus 40x. I get minus 15. I get minus 40x. So I get a final answer of negative 80x and 32 minus 15 plus 17. All right, let's multiply. Multiply these first. So this is still just y. I'm foiling. I get a 12. I get plus, whoops, 32, sorry, plus 32x with my outside product. I get minus 15x with my inside product, and I get minus 40x squared. Or y equals negative 40x squared plus 17 x's and a plus 12. So now the derivative, dy dx. Don't start putting dy dx here because this is still just y. Now the derivative is negative 80x plus 17, and the derivative of 12 is 0. And it's nice to see that we got the same thing for both. Okay, let's take a look at number 5. This would actually represent the last page of your first test. We'll certainly get through this. We'll see how we're doing on time. We may get beyond this. Find dy dx. Algebraically simplify your solution. Remember, many times it is easier to simplify prior to differentiating. Not so certain what we would simplify here, though. So I think this is straight quotient rule. Dy dx is low d high minus all of high d low over the square of the thing below. Low d high minus high d low over the square of the thing below. Definitely some easy simplification going on here. I get 2x minus 6 minus 2x minus, that's the heartbreaker right there, minus 1, all on square of the thing below, x minus 3 squared. For a solution of 2x minus 2x 0, negative 7 on x minus 3 squared. It'd be nice to just wrap that up. Dy dx, tie it all together, equals negative 7 on x minus 3 quantity squared. No real benefit in foiling that out. Okay, now B. This is a quotient with a product in it. So if I was not going to super foil this out first, I would get low, that's easy, times d high, yikes, not excited about that, minus high, it's all right, but I'd still have to super foil then anyway, times d low. If I'm going to simplify this, I'm going to have to super foil this thing anyway. Might as well try it first. So let's try this guy in our head. This is still y equals. I'm not finding derivatives yet. The only place I'm going to get an x cubed is right here. Then I'm going to get x squareds. I'm going to get minus 3 of them here, and I'm going to get plus 3 of them there. So my x squareds cancel. Well, that's good. How about plain old x's? X to the first. I get 9 of them here, and I get minus 9 of them there. Those cancel. So I'm down to plain old numbers, plus 27 on x cubed. Well, that was certainly worth doing first. And now we could quotient rule. Or we could say, wait a minute, couldn't I write this as x to the third on x to the third plus 27 on x to the third? And end up with y, still just y, equals 1 plus 27 on x to the third, or even 27 x to the negative third. Now if I dy dx that, take the derivative of this guy, the derivative of 1 is 0, the derivative of this becomes negative 81 x to the reduced by 1 negative fourth, or dy dx is negative 81 on x to the fourth. Not too bad. This guy. The only thing about this that I might prefer derivatives work really well with exponents compared to roots. So I might want to just be thinking of this as 4 on x to the 1/2 minus 1. Okay. So I'm gonna quotient rule this guy now. So I'm taking the derivative, dy dx. Can I just use y prime here? No, not really. Prime dy dx. Dy dx equals low x to the 1/2 minus 1 d high. But d high is the derivative of 4, that's 0. Minus high, 4. D low, the derivative of x to the 1/2 is 1/2 x to the negative 1/2. All on the square of the thing below. So certainly we would simplify that. Negative 4 times 1/2 is negative 2 x to the negative 1/2 on x to the 1/2 minus 1 squared. That could become, since we have a negative exponent, I can drop that factor to the bottom, equals, so I'm just going to repeat dy dx again, equals negative 2 on x to the 1/2. I'm going to write that first, and hopefully some of you are recognizing right now that I am not matching conventions. Much like math problems, if you're given a question that includes fractions, your answer should typically include fractions, not decimals. So the convention established here is, hey, we're going to use square roots. So better solution, because of the presented convention, is negative 2 on root x times root x minus 1 squared. But I liked working with that 1/2 exponent as I was finding the derivative. You can take a look, give it some thought. You might think foiling this out is good, but what a lot of people do, when they see a square root and a square, they say, oh, well, that's just x plus 1. No, you'd still have to foil this versus itself, and I don't think you're going to get it to look any prettier than what we've got right here. I like it. Okay, your answer should only have positive exponents. My answer should, but that doesn't mean I might not want to work with them. I could quotient rule this. I could quotient rule this and simplify, but I could also temporarily say this is 2x to the negative 3rd minus 7x to the negative 5th, and dy dx that. This isn't dy dx yet, this is still just y. dy dx then would be the derivative, negative 6x to the negative 4th plus 35x to the negative 6th, or final answer, dy dx is negative 6 on x to the positive 4th plus 35 on x to the positive 6th. Should I get common denominators, multiply this by x squared on x squared and combine? I would suggest, no, you probably shouldn't. Because kind of the convention here says, hey, we're not combining these. Why wouldn't, you know? Now, you could have done that. You could have made this 2x squared on x to the 5th combined and quotient ruled. And I'm not saying the other is wrong. I'm just saying this is the kind of in the form that they gave us the question. Let's answer it in that same form. Okay, this would be a logical place to stop, but I do have some time. This would be the end of day 1 test. I'm going to continue on this, and I'll note that. So it'll be easy for you to tell that this video also contains the beginning of day 2. Find the equation of a line perpendicular to the tangent to the curve when x equals 1. I need 2 things for an equation of a line. I need a slope and I need a point. My point is going to be 1 something. 1 what? Well, I need, if I call this f of x, I need f of 1. F of 1 would be 1/3 times 1 to the 3rd minus 2 times 1 squared plus 3 times 1, or 1/3 minus 2 plus 3. That's 3 1/3 minus 2. That's 1 1/3, or 4/3. My slope is based off of my slope formula, f prime x equals 3 times 1/3, 1 That's x squared minus 2 times negative 2 minus 4x plus 3. There's my slope formula, but I want my slope when x is 1. 1 squared minus 4 times 1 plus 3, or 1 minus 4 plus 3, or 4 minus 4. Slope is 0, so right now I would want to say my equation is y minus 4/3 would equal 0, except I want perpendicular. Oh, okay, so I need the opposite reciprocal of 0, but the opposite reciprocal of 0 is undefined. So I need some interpretation here. If it's undefined, that means the line that's undefined would be vertical. I've got a graph that's going through the point 1/4. The tangent line is here, but perpendicular to the tangent line is this line. This is the line I want to talk about, and that is the line x equals 1. Not certain that's going to happen on the test. We might just get a nice normal slope, but we should be able to interpret. Okay, number 7. These are really pretty quick problems. They're kind of cool. I don't know very much about the function of u other than when we've got, and this should be 4, by the way. U's graph at 4, we're up 1. There's no sense really in graphing it. It doesn't help you for this problem, but I'm going to go ahead and do that anyway, just to give you some sense of what's going on. When I put 4 in, we get 1. So we've got a point right here, and the slope there is like -2. So for an instant, the slope is -2 there. This, again, that won't really help us with this, but I just want to make some sense out of this. Then I've got a function v that at 4, we're actually down 7. And as we pass through 4, we have a slope of 9. It's really, really steep for at least an instant right there. But, as I said, just kind of giving you some context to this problem. This says find the derivative of function u times function v, or function u and function v's product. Therefore, by product rule, that would be first function times the derivative of the second plus the derivative of the first times the just plain second. Or, you just got to be careful here. We want plain old u at 4. U at 4 is 1. We want b's derivative at 4, 9, plus u's derivative at 4, -2, times plain old v at 4, -7. So I get 9 plus positive 14, or 23. Quotient rule. Low d high minus high d low over the square of the thing below. So I get plain old v, -7, u prime, -2, minus plain old u, 1, minus v prime of 4, 9. All on. So make sure these are all different, unless this was a 9 as well, or this was a 9 as well. Make sure these are all different, and you didn't copy something down wrong. All over plain old v, -7 squared. So let's see, I get 14 minus 9 on 49, or I end up with 5 on 49. Final answer. All right, same thing, but now we are low d high, or v on u instead of u on v. Low d high minus high d low over the square of the thing below. So let's see. Well, let's put in our values. U, plain old u is 1. dv, v prime is 9, minus plain old v, -7. du, derivative of u, is -2. All on plain old u squared. Take your time, set those up, make sure your values are correct. Notice here, if I'm doing this low d high minus high d low over the square of the thing below, these should always be the same. Low, low. All right, so I get 9, 3 negatives are negative, 9 minus 14 on 1, or 9 minus 14, -5 on 1. Okay, this could be thought of as 2 times the derivative of u minus 4 times the derivative of v minus 3 times the derivative of uv. But that's a product. So that is 2 times derivative of u, if we're looking up above, is -2, minus 4 times derivative of v is 9, minus 3 times. Now, if I didn't already do problem number 7, I'd have to go u times v's derivative, but put a big bracket here or something, u times v's derivative plus u's derivative times v. But we've already got that now, 23. We did that. We trust our work. So we get -4 minus 36 minus 69, or -40 minus 69, -109. Sorry, didn't have that one in view. Okay, so first 5 pages, quick preview. Let's do problem 8. Still got a little bit of time left here before my next class, so I'm going to get problem number 8 there, and then I believe I'm going to stop at that point. The position of a particle moving along the x-axis. So for me, that's always just a squirrel on a wire, just running around on that wire somewhere. At any time is given by this. This is our position. We got to be careful. Even if that was v of t, they said it's position. If you want to think of that as s of t, great. We typically talk about position with s, but x of t is our position. Find the times when the particle, or our squirrel, is momentarily at rest. Now, I could take a snapshot of the squirrel's position and then an instant snapshot right after it and see if the squirrel's moved. But what I'd really like to be looking at is the velocity. This is asking, if this is part A is asking, when is the velocity equal to 0? So I want the velocity formula. Velocity is the first derivative of position. So that is 3t squared plus 4t minus 7. So I want to set 3t squared plus 4t minus 7 equal to 0 to see when the velocity is 0. It'd be nice if that factors of -21 that add up to 4. There are 7 and -3. I can get a -3 from my outside product, 3t times t, -1 times plus 7, and a +7 on my inside product. So I get t equals 1 and -7/3. And my first thought there is, hey, I don't even know if t can be a negative value. We take a look, and it doesn't imply that it can't be. So t can be a negative value, so particle LE is at rest at 1 second and -7/3 seconds. Okay. So find the times when the particle is momentarily at rest. That's A. B, moving to the left. Okay, so now I'm going to just make a little line graph for a moment here. I'm going to put 1 second. At 1 second, our velocity is 0. At -7/3 seconds, our velocity is 0. And now I want to know when it's moving left would be when the velocity is negative. So I'm going to test my 3 zones. I could put 0 into velocity here. If I put 0 into my velocity, I get 0, 0 minus 7, and it's negative. I can put 2 into velocity, and I get 2. That's 4. 12 plus 8, 20 minus 7, it's positive over here. And I could put -5 in, or -3 in. See what happens to the left. It's going to be positive. But my velocity function is a quadratic, which means the graph is a parabola. If I graph this, this is an upward parabola. Velocity is positive here. This parabola would look something like this. And take a look. Velocity is up, it's positive. Velocity is down, it's negative. Velocity is up, it's positive. Therefore, my squirrel is moving to the left. B is moving to the left when t is less than negative 7/3. Should it be less than or equal to? Oh, that's wrong. That's wrong. I'm sorry. That's a mistake. Moving to the left when the velocity is negative. So that is negative 7/3 is less than t is less than 1 second. Could put seconds on each of those. We need to be between there. Now, should I use equals? I shouldn't use equals because at 1 second, my squirrel or the particle is temporarily at rest, just instantly at rest, but we're moving left during that time frame. And C, when is it moving to the right? Not a bad idea to notate. C, it's moving to the right when, I'm just going to make a quick note here, when velocity is positive. Could have done the same thing for this. We'll have to talk more and more about the little notations are kind of safety nets on the AP test. So when is it? That would be when t is less than negative 7/3 seconds, or when t is greater than 1 second. Okay, we can put those in normal notation as well, but that should do it for us. Okay. I know I said I was going to stop, but I think I'm in good shape on time here. So, still part of this is second question. Actually, this is second question, second page, day 2. On Earth, if you shoot a paperclip 64 feet straight up into the air with a rubber band, so that thing goes up and it comes straight back down. Goes up, comes straight back down. Stops for a moment, it's going up, stops, comes back down. Stops for not even a moment, an instant, and comes back down. But if we introduce time, that turns this thing into this function, which is if I was to graph this, this is actually a parabola. So as time's ticking off, it reaches its height and comes back down. So typically on these types of questions, we want to know when's it going up, when's it going down. We want to know how long does it take to reach its maximum height, or what is its maximum height. We're typically going to be dealing with the derivative. We're just supposed to find the first derivative of this right now. So ds dt, because they ask us to find that, is the first derivative of this function. So that would be 64 minus 32t, and d2s, second derivative of s, with respect to time, is derivative of 64 is 0, and this is the derivative of negative 32t is negative 32. That's a constant acceleration. Now that's all they ask for here, but I might make a note to myself here that, hey, this is velocity with respect to time is negative 32t plus 64. This is just a note for where I'm expecting we're going, and acceleration, second derivative, is just negative 32. Might not need those, but let's see. How long does it take? What am I looking for? Time. For the paperclip to reach its maximum height. Its maximum height is the top of that parabola. The top of that parabola right here that's created. And the top of the parabola, what part do we want? Do we want what's normally the x or what's normally the y? How long does it take? We want t. We want this value right here. And if we're not using a calculator and graphing and doing second calc max, we could find that by saying, well, I know what happens at the vertex. So one way we could do this is just say, well, the x-coordinate, or in this case the t-coordinate of the vertex, always happens at negative b on 2a of position. I'm going to rewrite this function. S of t equals negative 16t squared plus 64t, and if you like, plus 0. So I've got my a, b, c. So negative b on 2a would be negative 64 on 2 times a, negative 32. That is 2 seconds. That's our t value. It happens there. Now, we could also see what we've got here. We've got a parabola, and a parabola is a quadratic, or a parabola is totally in our wheelhouse. So many ways we've learned to deal with those. But if this wasn't a parabola, let's say it was a 5th degree or something, what they'd be looking for would be a maximum we're looking for where the slope is 0. And the slope equation is our velocity. We want when is the velocity 0? When does this paperclip go up and instantaneously stop? So I also could have said when is velocity equal to 0? And that would be 0 equals our velocity, negative 32t plus 64. So 32t equals 64. And once again, t equals 2 seconds. So either way, doesn't ask to do it both. With what velocity does it leave your hand? Well, when it leaves my hand would be find the velocity when t equals 0. No time has transpired. So that is saying find v of 0. Not when is the velocity 0, but what is the velocity at time 0? Well, v of 0 would be negative 32 times 0 plus 64, or 64, fill in those units. What are we dealing with here? Feet per second. Okay, I am going to stop there. We really just have 10, 11, and then some trigonometry type problems to take a look at the second half of day 2. So there will be a second video on that. Stay tuned. Good luck.